Welcome back. Today we're going to have a discussion introducing the mole. The mole is going to be crucial for any calculation that we do from here on out because we're not going to be able to compare gram of one type of element to gram of another one. The thing that keeps them in common is going to be the mole. And so what the mole is just a huge number. It's a huge number of particles, and that huge number is called Avogadro's number. And Avogadro's number is based on carbon. And it's said that if you have 12.01 grams of carbon, you've got 6.02 times 10 to the 23rd atoms of carbon. Basically, you can have a mole of anything. You can have a mole of carbon, a mole of nitrogen. You can have a mole of pennies, which would be really nice because then that means you would be really rich because that number is so huge. And since atoms are so small, you can see why we're going to need that large of a number. Now, to give us a perspective of how big a mole is, basically the volume occupied by a mole of softballs would be the size of the Earth. And so that tells you right there it takes a lot. It'd take a lot of softballs. And finally, if you had a shot put, if you had a mole of shot puts, that would have about the same mass as the Earth. So remember that the mole is a big number. That's another reason why scientific notation is so useful. You don't want to be writing 23 zeros. So now let's take a look at some calculations that we're going to do dealing with the mole. Now if I wanted to know exactly how many sodium atoms are in 0.12 moles of sodium, we're going to have to use our conversion factor. And our conversion factor is that 1 mole is equal to 6.02 times 10 to the 23rd. So 1 mole of sodium atoms would equal 6.02 times 10 to the 23rd atoms. All right, so I'm going to have to use a pencil because we're going to be using small numbers now. So let's see if I can write it nicely. All right, so we're going to start with what we're given, which is what we always do. So I've got 0.12 moles of sodium. And I'm going to convert it from moles to atoms. So we set up our ratio. The conversion factor is 1 mole equals 6.02 times 10 to the 23rd. So I'm going to put the 1 mole in the denominator. And the reason that I do that, and I really should have labeled this atoms, is equal to 6.02 times 10 to the 23rd sodium atoms. Now the reason I set up my ratio like this is you'll see that the mole of sodium atoms cancels out. Now I have two numbers in the numerator, so I'm going to multiply those two together. And when I multiply those two together, I get 7.22 times 10 to the 22nd, and that would be atoms of sodium. Now let's take a look at it. Oh, I got something wrong here. If you look at that, can you tell me, I've got the units, it's atoms of sodium, but how many significant figures are in that value? And you can see that there are 2, which means my answer really should say 7.2 times 10 to the 22nd. Now Avogadro's number, that 6.02 is not an exact number, so that actually has 3 significant figures. Atoms of sodium. I'm sorry my handwriting's so sloppy. I'm trying to get used to this this bamboo tablet. Okay, now we're going to take a look at the next example, and on this one we're going to go from atoms to moles. My conversion factor is that in every 1 mole of potassium atoms there's 6.02 times 10 to the 23rd atoms. So we start by what we were given, and I was given 1.25 times 10 to the 21st atoms of potassium. I need to set up my ratio. Now am I going to set up the ratio the same exact way that I did the one up above? And the answer is no, because I want to find it in moles. So I have 1 mole of potassium atoms. Has a value of 6.02 times 10 to the 23rd atoms of potassium. And you'll see that the atoms of potassium cancels out. So now what will I do with these two numbers? Now I'm going to divide those two numbers, and when I do that, I'm going to get, how about 2.08 times 10 to the negative third moles of potassium atoms. Okay, let's check our significant figures real quick. I have 3 there. I have 3. My answer can have 3. I've got a unit. I'm all ready to go. Let's see if I can get a little less sloppy in the next one. Okay, now this is different because now I'm asking how many carbonate ions are in 2.265 moles of aluminum carbonate. Okay, let's start with what we've given. And we're given that we have 2.265 moles of aluminum carbonate. First thing I want to do is, can I find out how many? Those aren't really molecules. Since it's an ionic compound, it's formula units. I'm not going to have enough room to write that, so I'm going to write down that 1 mole of aluminum carbonate that's a 3. There are 6.02 times 10 to the 23rd. They're not molecules, so they're formula units, but I'm just going to leave it as aluminum carbonate. Okay, I've converted it to the units of aluminum carbonate, but I didn't ask for that. I asked for how many carbonate ions. So this is going to add an extra step because I want to go from aluminum carbonates to carbonates. And I'm going to have 3 carbonate ions and every 1 aluminum carbonate. So now I have to take it another step. And now when I multiply those all out, let's see what we get. All right, so how many significant figures do we have here? This guy's got 4, this one's got 3. That's not going to be included in significant figures, so my answer can have 3. I throw it in my calculator and I get 4.09 times 10 to the 24th carbonate ions. Okay, that's how many is present. You'll see that I have 3 times the number of carbonate ions because there are 3 carbonate ions in every aluminum carbonate formula unit. All right, last but not least, let's try the next type of problem. All right, we're going to take a look at another type of problem. It's another 2-step problem. We're going to go from number of atoms to the mass of lead. Now, the thing that's going to be important to us is going to be, we always have to go to moles first. So we've got 2.25 times 10 to the 23rd, and that's atoms of lead, so lead atoms. And the first thing we want to do is find out how many moles that is. And that's where the Avogadro's number comes in. And in every 1 mole of lead atoms, there are 6.02 times 10 to the 23rd lead atoms. If I were to stop right now, my answer would be in moles. But I don't want moles, I want grams. So now we have to go use the molar mass from the periodic table, and there are 207.2 grams of lead in every 1 mole of lead. And the mole of lead atoms cancels out. And now I'm going to multiply everything in the numerator, divide by in the denominator. And I've got 3 significant figures here, 3 significant figures here, 4. So my answer can have 3. Let's throw this in their calculator. And I get 87.8 grams of lead present when you have 2.25 times 10 to the 23rd atoms. All right, last one. What if we do this instead? How many oxygen molecules are present in 0.47 grams of oxygen gas? We write down what we were given. We were given 0.470. That 0 is important because that's going to be a significant figure. First thing I want to do, I've got to go to moles. Have you noticed with all these problems, moles is critical. You cannot bypass this step. And every 1 mole of oxygen has a molar mass of 32.00. Remember, we always go to the 100th place on the periodic table. Okay, if I stop now, I have moles of oxygen, but I want to know atoms, or molecules, pardon me. I want to go molecules, and we know that every 1 mole of oxygen, how many molecules are present? And there's 6.02 times 10 to the 23rd. Okay, that is really ugly. Times 10 to the 23rd oxygen molecules. And that gives me a value of 8.84 times 10 to the 21st molecules of O2. And there you go. See you next time.